Hello, my name is Junli. I was in charge of fairness part in my team. So today I'm gonna present a paper named Fairness Without Demographic through adversarially reweighted learning. Please enjoy it. Recently, the problem of fairness in machine learning has emerged. For example, Compass, which is used to forecast which criminals are most likely to reoffend, shows racial bias that black offenders who are seen are almost twice as likely as white offenders to be labeled a higher risk, but not actually reoffend. In addition, for various applications, bias results were found for sensitive attributes such as race and gender. Therefore, many researchers have defined fairness in machine learning and studied debiasing techniques. However, the fairness studies conducted so far have problems. That is, most of researchers on fairness assume that they can access to protected features. However, the assumption is not true in real world because there are privacy and legal issues. So in many cases, we cannot collect or use sensitive information to train or inference our model. For example, SafePB requires that creditors should comply fairness, but creditors cannot use demographic information to decision making. So the authors represent the research question as how can we train a MM model to improve fairness when we do not have access to protected features? To answer the previous question, first we need to define what is fairness. Authors decide to use definition of Gaussian maximum fairness, which maximizes the minimum expected utility across protected groups. There is another fairness definition that parity-based fairness, but authors choose Gaussian maximum fairness because increased minority performance is more reasonable than just decreased gap among groups. Gaussian maximum fairness can be represented as first equation, where H is hypothesis and S is sensitive attributes. And authors replace utility function into loss function for ease of training because utility function, for example, AUC score or accuracy are statistical metrics which are not differentiable, so it is difficult to use in training. So the equation is changed like below, and because a loss function, which means negative effect in utility, so that min-max in hypothesis are changed. And bringing idea from re-adding and adversarial learning, the objective function can be defined as sum of lambda si multiplied loss of the model. And training is conducted by training theta to minimize the objective and training lambda to maximize the objective to focus on high weight data points. So prior works reweight based on protected group memberships to devise the model. However, in our case, we don't know protected group membership, so we cannot reweight based on protected group membership. And there is similar work with this paper named TRO, which aims to debias the model without protected group demographics. They set weight based on loss to focus on data points with larger errors. However, emphasizing high loss data points makes poor performance with noisy outliers because it can easily overfit to outliers which have high loss. So authors seek to information which is correlate with an observed protected group and more robust than loss. So they first hypothesize unobserved protected groups are correlate with the observed features and class labels. And they confirm it by inferring protected group from observed features and labels. The result is at the right table, and it shows that it is true within other LSAC dataset. And they find computationally identified region that an identifiable region of misclassified data points to utilize observed features and labels. For the explanation about computational identifiable region, let me give you an example in below figure. There are two protected groups which is classified by color, and the trainer cannot access to it. The result of ERM, there is an incorrect positive class cluster close to decision boundary, and that is computationally identifiable region. Data points in computationally identifiable region have high loads, but they are not outliers. So authors think that they can improve worst group, which is not outliers, by improving performance of data points in CI region. From this, authors propose adversarially reweighted learning, which is an optimization approach that leverages the notion of computationally identifiable errors through an adversary to improve worst-case performance over unobserved protected group S. In other words, they set weight lambda in objective function based on CI region. To utilize CI region information, they train classifier fpi to predict the data point is in CI region or not. So that they can emphasize data point in CI region. So the authors define lambda as 1 plus n multiply sum of fpi of all data points over fpi of the data points. This lambda is designed according to following design rules. First, they try to prevent negative value because negative loss makes training unstable. And second, they try to prevent zero weight to fully utilize all the data points. And last, they try to prevent exploding gradients by normalizing. To train an objective function which is zero-sum game between lambda and theta, ARL conduct a minimax game between learner and adversary, and train them alternatively. In detail, the learner tries to learn main classification test to minimize objective function, and the adversary tries to learn a classifier for CI regions to maximize objective function. Then learner can train the model which focus on data points in CI regions. For evaluation, they use following experimental settings. First, they use learner which has structure 2 layers fit4 network with 64 and 32 hidden units, and they use activation function for LELU. And adversary, they use 1-layer linear model. It is an interesting point because it is very simple model. They use this simple model because complex model can be overfitted into outliers like DRO. And there are baselines like code baseline, which is standard ERM with uniform weights, and GRO I previously mentioned, which locate more weights to larger errors. And they test on following that dataset named auto, which predict income prediction, which predict income, and SAC, which predict loss co-automation, and Compass, which predict recidivism. And the detailed of dataset is shown in table. And they evaluate methods based on following metrics. The first two metrics, AUC average and AUC macro average, shows overall performance of method, and the last two metrics, AUC mean and AUC minority, shows worst-case performance among groups. As a result, AR improved worst-case performance within other than LSAC dataset, so that it shows handling CI region data points in CI region can improve performance minority groups close to average of overall data, which means it improves fairness of the model. However, there is performance degradation within COMPASS dataset. So uh, in this point, authors argue that it is because protected groups in COMPASS dataset are not computationally identifiable, and even ground truth class labels are noisy. However, AR perform better than DRO even within COMPASS dataset. And um, and as I said, AR can improve performance of worst cases. So uh, it leads to AR improves overall performance too. And comparison with inverse probability weighting, which set weight to inverse of probability, ARL outperformed than IPW with other than LSAC. Even IPW knows protected attributes. Because ARL selectively outweight incorrect protected groups rather than outweight all the data points. And compared to group fairness approaches, experiments show that group fairness approach can reduce gap between groups, but does not always improve worst of groups. But ARL can improve worst of group always. And there are some analysis to understand ARL. ARL. Previously, we checked that ARL was poor with COMPASS, which has noisy labels. So they test robustness of ARL within to aspect representation bias, which means bias in group size, and label bias, which means there is incorrect labels. The results show that both DRO and ARL are robust to representation bias and, sensitive to label bias. About this, authors say that DRO and ARL are sensitive to label bias because they outweigh using prediction error, but they cannot distinguish whether labels are true or noisy. And they investigate ways from ARL is meaningful. The visuals show that weights in ARL successfully reflect whether example is misclassified or not, and whether uh, it is class imbalance examples or not. And additionally, I tested changing model in the adversary to increase capability to find difficult CI regions. For example, encompass uh, more uh, more precisely and with a little with a little overfitting. And results show that complex model perform better than simpler one with other than LSAC. However, within Compass, which is goal to design this experiment, uh, it cannot improve performance, and even it degrade the performance. So the experiment result show that like Compass, that whose data are not computationally identifiable and noisy, which who has noisy label, cannot be resolved by just increasing model complexity. So in summary, authors proposed adversarial reweighted learning to improve model fairness without accessing protected demographic. ARL can improve model performance for worst-case protected groups, and ARL is robust to noisy outliers because it focused data points in CI region. Uh, this is the end of my presentation. Thank you for listening.